This is Professor Belton. This is Algebra 2, Chapter 5, Section 6, Inverse of a Function. So what I'm going to do here is write a formula for the input of a function, So basically you want to solve for x, because normally you plug in x and get y. I want to plug in y and get x, essentially. So to determine the input when the output is 7, right? Because your output is y. So the question is, what is the x, the inputs? We're kind of working in reverse. So y equals 2x plus 3. That is our original. Okay, so we'll take y equals 2x plus 3, and we'll solve for x, where this is the function notation. This is the equation notation, which are equivalent. We'll be going back and forth throughout the lesson. Okay, so add subtract step, minus 3. So y minus 3 equals 2x, and divide by 2. So we get a final of x equals y minus 3 over 2. Okay, so you want to plug in the output, which is negative 7. So x equals negative 7 minus 3 over 2. So we get negative 10 over 2. So we get negative 5. So essentially negative 5, negative 7 is a coordinate. Okay, pause the video, try the 3 student problems. Okay, so again we're given an output of 2, so that is our equivalent y. And we want to know, what is the input? X, question mark. So our original here is y equals x minus 2 for the function and equation notation. So there's our original. Okay, so y equals x minus 2. We'll add 2. So x equals, I'm sorry, I wrote that backwards. So y plus 2 equals x. So x equals y plus 2. If you write it in terms of the output, which is what we're doing here. So plug in the output. So x equals 2 plus 2. So x equals 4. Thus there is a coordinate 4, 2 with this function. Okay. All right, we'll move this down a little bit for the next one. Alright, so the original is y equals 2x squared. So y equals 2x squared, so we'll divide by 2. So y divided by 2 equals x squared. We're square root both sides, which is incorrect, because if you square root an even root, it's plus or minus. So you get x equals plus or minus the square root of y over 2. Okay, so we want to plug in the output of 2 again. So y is 2. So we get x equals plus or minus the square root of 1. X equals the plus or minus 1. So therefore we have 2 coordinates. We get 1, comma 2, and negative 1, comma 2. Okay, we have 2 possible coordinates here. Okay, I think it makes sense because it's a parabola, right? You're going to have equidistant points on both sides. Okay, last one. So the original is y equals negative x cubed plus 3. There's the original. Function and equation notation. So y equals negative x cubed plus 3. So add subtract step is minus 3. So y minus 3 equals negative x cubed. So next thing we need to do is multiply, divide, but that's really a negative 1, right? So we're dividing by a negative 1. So negative 1y plus 3 equals x cubed. And now we'll do the exponent radical step. So cube root of negative 1y plus 3 equals the cube root of x cubed. Gives us x equals the cube root of negative y plus 3. Okay, and lastly we want to plug in an output of 2, which means y is 2. So x equals the third root of negative 2 plus 3, because we're plugging in the 2. So x equals the third root of 1, which is 1. Therefore there exists a point of 1 comma 2 on this function. Okay. Alright, page 2. So essentially what we've been doing the whole time is working with inverse functions. Essentially when you flip the input and the output, you get an inverse function. So we take a basic line of 2x plus 3. You can make a table of values of negative 2, negative 1, 0, 1, 2. And if I plug them in, if I plug in negative 2, I get negative 1. And thusly, plug in negative 1, you get 1. You plug in 0, you get 3. You plug in 1, you get 5. You plug in 2, you get 7. You can prove that to yourself by continually plugging in the numbers, or just graphing accordingly. So negative 2, I get negative 1. At negative 1, I get positive 1. At 0, I get 3. At 1, I get 5. And 2, I get 7. Let me fix that one point there. It's a little off. But nonetheless, there is our line. And a little curvy on the end there. Nonetheless. Okay, so essentially, if you flip the table, you get the inverse function, which they're calling g of x here. So I should be able to flip this around and do negative 1, 1, 3, 5, 7. Are we really sure that that can just flip the x though to the y? Well, let's try. So if I plug in negative 1, I get negative 1 minus 3 over 2, which is negative 4 over 2, which is negative 2. Huh, that seemed to have worked, right? Same number, right? Try that. We'll try one more. So we'll try g of 1. So that's 1 minus 3 over 2, which gives me negative 2 over 2, which is negative 1. So that seems to have worked, so we can just flip the table accordingly. So at negative 1, I'm at negative 2. At 1, I'm at negative 1. At 3, I'm at 0. At 5, I'm at 1. And 7, I'm at 2. Okay, so that's my g of x. That is my f of x. And what you notice is the values are symmetrical on this line. That line is y equals x. And why is it symmetrical on that line? Because you look at it, we're switched the y and the x values. So if you switch, you should be symmetrical or flip over that line. Okay? Let's try a problem. Okay, so the original function is 3x minus 1, so we turn that to equation notation. That's 3x minus 1. So that is the original function. Okay? One's in the function notation, one's in the equation notation. So to get the inverse, we need to switch. So we'll change colors here to a red. So we get x equals 3y minus 1. So we flip the x and the y, and we'll solve for y. So we'll add 1. So x plus 1 equals 3y. And divide by 3. So the add subtract step. Multiply, divide. So we get y equals x plus 1 over 3. So the correct notation is f of negative 1 of it. Whoops, that didn't work out. F of negative 1 of x equals x plus 1 over 3. So that is the inverse function. So that does not mean -1 exponent. It's a notation for inverse. You'll see the same thing in trigonometry for sine, cosine, tangent for inverses also. And you'll notice it on your calculator as a -1 power and a -1 power for trig, because that is a notation for inverses. The book will use g of x sometimes to rename the function, but that is the proper notation to use the -1. Okay, try the next two problems. Okay, so we'll try the next two. So the original, let's go back to blue, is y equals -x plus 1. That is the original in function and equation notation. And the b is y equals 1/2 x minus 2. That is the original. Okay, so we'll get the red now. So the inverse, we need to switch the variables. So x becomes -y plus 1. So we'll subtract 1. X minus 1 equals -y, which is really -1y, right? And we'll divide by -1. So y equals -x plus 1. So using the proper notation, f of -1 of x, which means inverse, is -x plus 1. So that is the inverse function of the original. Okay, so this one, x equals 1/2 y minus 2, so we'll add 2. So x plus 2 equals 1/2 y, and we'll times both sides by 2. So that gives me y equals, if I distribute, 2x plus 4, so using proper notation, f of inverse of x equals 2x plus 4. So these are inverse functions of each. So again, it accomplishes what we did in page 1. Or if you plug in the output, you'll get the input, which is very handy. Inverses are used in computer programming to undo something that was done prior. That is the end of part 1.